Where we left off in the last video was we just seen an example of resonance where when we used a sinusoidal forcing function on a mass on a spring without resistance, such that the frequency of the forcing function was just right, then this phenomenon called resonance occurred. And I want to analyze this in some more detail now. So we consider, as always, the mass on a spring equation, but for now we're going to not consider resistance, so we'll just assume we have a mass and a spring constant and a forcing function of the form a sine omega t. And similar things happen if you use cosine. The sine or cosine is not important. The complementary solution, which you obtain by solving the associated the complementary homogeneous equation where you replace the right-hand side with 0, the solution you get is this. That's from solving the characteristic equation mr squared plus k equals 0, which gives you that r equals plus or minus the square root of k over mi, which through Euler's identity leads to what you see here, as discussed in our video on homogeneous equations. So this quantity here, the frequency of the homogeneous equation, root k over m, is called the natural frequency of the system, and I like to give it the name omega naught for the to indicate that it's a sort of frequency omega, but it's somehow intrinsic to the system. So it's a specific number, root k over m. And we can write, if you apply the trigonometric identity for combining cosines and sines, you can combine them into constant times cosine omega naught t minus phi. And then, alright, so that's the complementary solution. But anyway, so you can rewrite this as this if you choose. But then we also need to consider the particular solutions of this problem by solving the inhomogeneous equation. If omega is close to the natural frequency omega naught, then beats occur, and if omega equals omega naught, then we have perfect resonance. There are homework problems on this, and I've already introduced you to it in the last video. But the homework problems on the website ask you to, I believe you'll be studying this phenomenon with resistance as well. So you'll see how this stuff changes when we. So we'll take a look at the problem of resistance before I send you off to finish it on your own. Particular solution to the mass spring system with resistance. So let's consider this problem. I'm calling this m now for the amplitude of the forcing function. So let's assume then that we have a mass on a spring and this forcing function, and we're going to solve it, or at least find a particular solution to this problem. So we're not going to worry about initial values. The characteristic equation is this, which gives us the roots shown here by the quadratic formula. So the complementary solution, it's going to involve an exponential function. And now how do I know that? Well, recall that the complementary solution is e to the rt. And for both of our roots, minus beta over 2m plus the square root and minus beta over 2m minus the square root. For either one of these roots, we have a real part, minus beta over 2m. And that real part corresponds to an exponentially decaying part of our solution, e to the minus beta t over 2m. So the complementary solution is always going to be exponentially decaying. If this square root is, if we're taking the square root of a negative number and we end up with an imaginary part, then we end up with an exponential times a trigonometric function. Whereas if we get a positive thing in the square root, then we just have two real roots, and they'll both be negative, so we'll just have exponential decay for our complementary solution. In either case, we always have exponential decay for our complementary solution, so there's no danger of resonance occurring, of pure resonance occurring, because we can, when we're solving the inhomogeneous equation, we're going to end up guessing that our particular solution is a combination of sine omega t and cosine omega t, and this guess will work. It's not going to conflict with our complementary solution. We use a computer to do the algebra, so we define our particular solution to be what I wrote here, and then we plug it into the differential equation and simplify, and we end up with this expression, a bunch of constants times cosine omega t, plus a bunch of constants times sine omega t. And then if we want this to equal m sine omega t, then we need all this stuff to equal capital M, and all this stuff to equal 0, as I've written here. Now k, lowercase m, omega, and beta, those are all constants that were supposed to be given in this problem. They would be empirical constants, numbers. What's unknown is capital A and capital B. We can solve this for them just using a computer. So we plug these equations into our solve function, and I also simplified the answer, otherwise it's kind of ugly. Yeah, I'm not really quite sure why Mathematica doesn't just automatically simplify solutions. I'm sure there's some reason, but anyway, use full simplify to clean things up. Otherwise this turns into a bit of a mess before it simplifies. Anyway, you get these values for A and B. So we were trying to find a particular solution to this equation, and we found it, provided we take A equal to this mess and B equal to this mess. But it's not really a mess, they're just numbers. All these letters here are just given constants in the problem, so they boil down to just numbers. Then we can rewrite our solution as using the trigonometric identity, c cosine omega t minus phi, where c is the square root of a squared plus b squared, and phi is the arctangent of b over c comma a over c, where I'm referring to the two-argument arctangent function, documentation for which is in Mathematica. It's the same as taking the arctangent of a over b, except it also provides you with an angle that's in the correct quadrant. That's the only difference. Anyway, note that we have a nice expression for the amplitude. That's capital C, which is the square root of a squared plus b squared. Actually, if you simplify it down, you end up with this, which is not quite as bad as you might have expected. So this is our expression for the amplitude of our particular solution. And if the resistance were 0 and omega were equal to omega naught, where recall that omega naught is, in that case, it's the square root of m over k. That's my definition of omega naught in the case of no resistance. Then you'd end up with pure resonance. You'd end up dividing by 0 here. And so you'd have an infinite amplitude, so to speak, which makes which matches what we saw, that the amplitude was increasing forever in the last video. So yes, so this amplitude expression doesn't make sense in the case of pure resonance, or it does make sense, but it's a divide by zero, giving an infinite amplitude. So we have this differential equation. We found a formula for the amplitude of the particular solution, and it was this. If we suppose we fix the mass, the resistance, the spring constant, suppose these are all given to us. And then I ask the question, for what value of omega, that's the frequency of the forcing function, for what value of omega do we get the largest amplitude? If we call that value omega 1, it's called the optimal resonating frequency, and the resulting amplitude is the optimal resonating amplitude. So this situation is a lot more complicated because of the beta, the resistance. In the case where we didn't have beta, where the resistance was 0, the optimal resonating frequency was the natural frequency, the square root of k over m. But now that we have resistance, the situation's a lot more complicated. And we can't ever get pure resonance, but we can get optimal resonance by choosing the optimal value of omega. So I ask you in the homework to figure out what value of omega maximizes this amplitude. That's a calculus 1 problem when you think about it, because all the other numbers are fixed, so it's really a function of one variable, omega, and I just want you to use calculus 1 to figure out what value of omega maximizes this whole expression. Actually, there's the answer, so I'm really more asking you to show that this is the correct answer. But this is only the correct answer if 2km is larger than beta squared. Otherwise, this wouldn't make sense. And in that case, where 2km is smaller than beta squared, the optimal resonating frequency is 0. Now, I'm not going to say any more about this. I want you to think about why that's true, why that would make sense, or what exactly is trying to be said here when I say that the optimal resonating frequency is 0. This is the case where we have a resistance that is large enough that it prevents any kind of resonation from occurring at all. So there's an example of this now, this result. Suppose we have a car that we expect to drive on a bumpy road, has shock absorbers, which makes this car a mass on a spring. And as the car varies its speed, the shock absorbers are subjected to varying frequencies, omega of input force, of amplitude 1000 newtons. Supposing that the mass of the car is 5,000 kilograms, 5 metric tons, the spring constant is 3.2 times 10 to the 6th, and supposing that the resistance on the spring, the resistance to motion is 400 kilograms per second, then at what frequency does the shock oscillate with the largest amplitude? Well, this is really just a question about what the optimal resonating frequency and optimal resonating amplitude are. And using our result from the homework problem, first of all, we have to check that this is true, otherwise the answer would be 0. But since this is true, we conclude that this expression is our optimal resonating frequency, which is about 25 oscillations per second, 25 hertz, as this is called. And the optimal resonating amplitude is 0.099 meters, which means that if the car is driving at such a speed that the shock absorber is subject to this frequency and this amplitude of force, then you can expect the car to oscillate with amplitude 10 centimeters at so where did I get 4 hertz from? It's the hertz is if you have sine of omega 1 t, where omega 1 is 25, then the period is tau over 25. And then if you take the reciprocal of the period, you get the hertz, which amounts to about 4 hertz. So you can expect the car to be jostling up and down on the spring with 20 centimeter jolts 4 times per second, which would probably be catastrophic for the car, if I had to guess. But that's the worst possible oscillation that we can expect the car to experience at this in this situation. So that's pretty much all that I have to say on higher order equations, at least in terms of what's really important for you to know. So I'm actually not planning on testing any of my students on what follows. It's important to know that there are other applications of this stuff and other topics that warrant further exploration, just that we won't be covering in this course. One of the topics is electric circuits. If you have a battery, a resistor, an inductor, and a capacitor lined up in a circuit, then the mass on a spring, it turns out this can be modeled. It turns out the differential equation very similar. And for the amount of this is called a capacitor, what I've drawn here. It stores electric charge. And if you hook up the battery, resistor, inductor, and capacitor on a circuit, then the amount of charge on the capacitor, measured in a unit called coulombs, that's a measure of charge, satisfies this differential equation, where this script E is the voltage of the battery, or whatever. It could be an alternating current, so it could be a variable voltage. So you have this differential equation, which is almost exactly the same as a mass on a spring, except instead of m, beta, and k, we have L, R, and 1 over c. So you can solve this differential equation in the same way. It's just we have different units now. L is measured in henries, resistance is measured in ohms, capacitance is measured in farads, and the electromotive force is measured in volts. And there's a note here to not confuse capacitance with coulombs. It can be a little bit confusing, especially if you solve differential equations and get constants. You'd probably be better off not calling them C in this case. So you already know how to solve that equation. It's the same solution technique applies. If you compare them, you see it's really mathematically it's the same equation, just 3 constants attached to function second derivative, function first derivative, and the function. This is an example of an important concept in math and engineering and physics called dual systems, where if we have, in this case, a mass on a spring is dual to a capacitor in a circuit. They're modeled by the same differential equations, even though they're seemingly 2 different things. And we say these systems are dual to each other, seemingly different phenomena represented by the same differential equations. And finally, this brings me to a last topic called variation of parameters. that I decided we're not going to cover in this course, although it's a powerful technique, and it's even come up in my research. So I will teach it with an example. X prime prime plus x equals tangent t. Let's solve this. So the method of undetermined coefficients that I've taught you would suggest that you should guess that the solution is of the form a tangent t. Unfortunately, if you try that, you'll find it does not work. So we're at a loss here. What do we do? Well, we begin by solving the homogeneous equation. So you get cosine t and sine t for your solutions. Then recall that the general solution to the homogeneous equation has this form, c1x1 plus c2x2, which is this. So this is the general solution to the homogeneous equation when we put a 0 here. But how do we deal with the tangent? In variation of parameters, we replace the parameters c1 and c2 with functions. So we're going to search for a solution having this form, where we've replaced c1 and c2 with functions u1 and u2 of t. Now we're going to try plugging this into the differential equation. We get this just from the product rule. I'm just omitting the t's now, but it's understood that all of these things are function of t. And then if we make this sort of strange assumption that x1 u1 prime plus x2 u2 prime equals 0, if we just assume that for the moment, then these terms go away, and we're left with this for our first derivative. And then for our second derivative, we use the product rule, and then we plug in our function, its derivative, and its second derivative into the differential equation here, and we find that this would have to be true if we are to have found a solution to our differential equation. However, we notice that since x1 double prime plus x1 equals 0, because x1 and x2 are solutions to the homogeneous equation x prime prime plus x equals 0, we realize that this is 0 and this is 0 similarly, which causes a lot of this stuff to disappear. u1 x1 prime prime plus u1x. So this term plus this term equals 0, as well as this term plus this term equals 0. So we're just left with these two terms. So we conclude that this would have to be true if we are to have found a solution to our differential equation. So our goal then is to find functions u1 and u2 such that this is true and this is true. So to recap, we were searching for a solution of this form, and we found that it would be a solution provided it satisfies these two equations. We solve this system for u1 prime and u2 prime, and we get this. We simplify this, it becomes this, where I'm using the fact that x1 is cosine t and x2 is sine t. We can integrate both of these. For this integral, I used sine squared equals 1 minus cosine squared, or you can just use a computer. And since our solution is x1 u1 plus x2 u2, we conclude that our particular solution is, well, x1 is cosine, u1 is all of this, and then x2 is sine, and u2 is cosine, so we have a sine cosine minus sine cosine that cancel, and what we're left with is cosine t times this natural log with a minus sign. So that's our particular solution, and you can check that if you plug that into the differential equation, it in fact is a solution to the differential equation, which is pretty remarkable when you consider that the second derivative of this must be immensely complicated, or you would have expected anyway. There's no way we could have possibly guessed this solution, so the method of undetermined coefficients was hopeless in this problem, but variation of parameters allowed us to solve it. And it turns out variation of parameters works in general for higher order equations as well, provided we can solve the homogeneous equation, replacing this guy with 0. Once you solve the homogeneous equation, you just do the same thing. You assume that your particular solution will have the form u1x1 plus blah 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 all the way up to un(xn). So, and it turns out you can always find a solution of this form. So that's what variation of parameters is. And in the end, you end up finding out what u1 prime up through un prime are, and then integrating that to figure out what u1 through un are. So I have a reference here. I wanted to show you what variation of parameters can be used for. First of all, it comes up in some theoretical contexts. Basically, this is a theorem about equilibrium points for differential equations. It's about stability. And I just wanted to point out that the proof of this theorem uses variation of parameters to get a formula for something that it needed a formula for. So it's talking about inhomogeneous differential equations and using variation of parameters to solve them. So variation of parameters can be used in some theoretical contexts, is my point. Also, here's another example. This theorem says something about something called vector flow, where if you have a vector field and you want to imagine it sort of representing like a wind or water velocity field, then this theorem says something about how if you have a smooth shape like a circle, and then you allow it to flow downstream, it'll remain smooth. That's very roughly speaking what this theorem is saying. It won't remain a circle, but it will remain it'll remain a smooth shape. So that's what this theorem is saying. And the proof, let's see, it's very long, but eventually, toward the end of the proof, actually, variation of parameters is used to prove the existence of a solution to a certain differential equation. And remarkably, this implies that the smoothness result that I was just talking about. So this proof also used variation of parameters.